Good morning, good afternoon, and good evening. I'm Tom Concolino, and I'm here with our presenters, Angela Criswell and Aya Takase.
Hi, everyone.
Hi.
Thank you all for attending Rigaku's webinar series on X-ray computed tomography for materials in life science. This session is on refining segmentation using ImageJ. So this session will be taking place in the lab with Angela and Aya reviewing in real time how to refine image segmentation. Now, please note if you missed any of the previous webinars, you can view them on the Rigaku website. Before we start, a few housekeeping items. As far as today goes, this is going to be an interactive session. So we'll be taking your questions live during the webcast and answering them during the session. So please don't wait until the end to ask. And as usual, please submit those questions via the Q&A button at the bottom of your screen. I won't be monitoring the raised hand function, and I'll also be posting relevant links in the chat window. So we'll try to answer as many questions as we can during the session, and we'll respond to any unanswered questions after the session is complete. If for whatever reason you have difficulty viewing the webinar live, please note it is being recorded, and you'll be able to view the recording beginning tomorrow. And with that said, I'll turn it over to Angela and Aya.
Thanks, Tom, and thanks, Aya, and thank you to everyone who's joining us for this presentation. So today we're presenting live from our office in the Woodlands, Texas, where we'll be doing some interactive workshop with ImageJ. If by chance you missed our first workshop, because this is a second ImageJ workshop we're having, you can, Tom will post a link so that you can view it later. And that particular workshop was titled Processing Images with ImageJ. So feel free to view that at a later time if you haven't seen it already. All right, so today the things that we're going to cover is we're going to ask, why do you need to refine segmentation results? And secondly, we're going to ask, how do we refine segmentation results? And then finally, we're going to look at some examples using a plugin called MorphologiJ. And just like workshop 1, we're using the Fiji distribution of ImageJ, and that operates on Windows, Mac, and Linux. Also, what we're going to do is we're going to be using a plugin called MorphologiJ, and this was developed by a group in France at the IJPB Modeling and Digital Imaging Lab. So you'll get links for those from Tom as well. And if you've downloaded the data, you can follow along. Otherwise, just sit back and watch, and you can follow along with the recording. All right, so then let's get started. So the ultimate goal of X-ray computed tomography data analysis is that we want to quantify some information about those features that we see in CT images. And to quantify features, we first need to segment the CT data. And during that process, each pixel or voxel within the CT data is given a label, and that assigns it to a specific region of interest. So great. And now the question is, why exactly do we need to refine these segmentation results? And that'll lead us to our first poll from Aya.
So let me start it. So as Angela mentioned, the first question we want to answer is, or think about, why do we need to refine image segmentation results? A, to correct the errors in pixel classification. B, to reduce artifacts in the image. C, to remove unwanted regions of classified pixels, or A and C. We're going to give you a few more seconds to think about. We're getting to about a half of you, I think, answering that question. Well, I will share the results, but nobody is selecting C so far. Okay, I think we got a majority of you voted, so I'm going to end the poll and share the results. So why do we need to refine image segmentation results? And the most popular answer was A and C, to correct errors in pixel classification, and C, to remove unwanted regions of classified pixels.
Okay,
Okay,
all right. So turns out that's correct. And we know there are many, many tools that we can use for segmentation, and these are thresholding, machine learning, and deep learning. And some are more powerful than others, but it can be said that no segmentation tool is absolutely perfect. If you want to learn more about data analysis and segmentation using machine learning in ImageJ, I'm going to ask Tom, he's going to put a post to some earlier webinars and workshops we had, so you can dive into that and see exactly how this works and why it's not always perfect. So because it's not perfect, some pixels are incorrectly labeled, and we need additional tools to fine-tune segmentation results. So to illustrate that, I'm showing a figure here of a foam sample, and thresholding is used to segment this particular image. And in this case, we assign polymer pixels as white and void pixels as black. And if we look at this, we can see that there are incorrectly assigned pixels. So specifically in the polymer area, we have some pixels that are labeled as void. So they're false positive for void. And inside the void, we have some white pixels labeled as polymer, and that's a false negative. So we need to refine these results. Additionally, we often want to further partition our regions of interest. For example, we may want to examine labeled regions within regions. So for example, here's maize, it's a corn cob. And what we want to do is to take our kernel region of interest, or ROI, and divide it into individual kernels. And once we do that, then we can make some quantitative assessments of the size of these, the volume distribution, and things like that. So other things we might want to do is we might want to exclude some regions of the ROI from our analysis or that intersect with the border. And luckily, there are many tools available for this post-segmentation refinement, and we'll use some of those today. So that leads us to our next question, exactly how do we do this? So there are many tools, like I mentioned, and the simplest and most common tools are called morphological operations. And morphological operations are commonly used, and we're going to have a look at those first. So a morphological operation, it works by probing an image with a structuring element to test how that structuring element intersects with the ROI. So we're going to illustrate how that works by looking at dilation and erosion. But before we do that, we're going to go to our next poll question.
okay. So the second question is, this is a true or false question. Dilation creates connection between shapes and erosion fills holes in shapes. Is it true or false? This one is a bit tricky, isn't it?
Mm-hmm.
I'm giving you a hint. It's kind of split half and half.
Yes, exactly.
Yeah,
Or both of them have to be
not
true.
a good hint, apparently.
Exactly.
It's making two statements. So
Statements.
Yeah.
Yeah,
I wonder if people can change their mind and change their votes.
I'm not sure.
Not sure.
Mm-mm.
Okay, so most of
Seems
you
like a pretty
voted.
even split.
Yeah, pretty even. Okay, I'm gonna end the poll in a few seconds. Okay, so that's about 80% of you. So I'm gonna end this and share the results. So the question was, is it true or false? Dilation creates connection between shapes and erosion fills holes in shapes.
All right.
The true was 8% higher.
Okay.
Okay,
Well, let's just interrogate those questions by looking at those operations. All right, so let's look at dilation first. So the principle of dilation is to probe this region of interest with this structuring element. In this case, we have a disc-shaped structuring element. And you want to ask the question of whether the structuring element and its origin, which is at the center, whether this structuring element intersects with the ROI. And if it does, then it's going to fill out to the point that you reach the origin. So here's an area where it shows that it's true. Out here, it's false. So there's no connection between the structuring element and the ROI. And here it's touching both little pieces or both islands here, and it's creating a connection. So dilation is going to result in a shape that's larger than the original ROI. And additionally, it's going to create connections between components. Also, if we had any holes inside of our ROI, those would be filled. So the first part of that question is actually true. Now let's look at the second part of our poll question, erosion. So alternatively, the principle for erosion is to probe the ROI to test whether the structuring element is fully contained within the labeled area. So this illustrates this right here. So we see the structuring element is fully contained here. And in this case, because this small island is smaller than the structuring element, it gets eliminated altogether. So erosion is going to result in a ROI that is smaller than the original. And additionally, it's going to remove small isolated objects or thin lines that are thinner or smaller than the structuring element. And it can also be used to separate two objects that may be connected by a thin line or neck. It does not, however, fill holes within the ROI. So it turns out that the answer to that poll question is false. The first part was true and the second part was not. One of the other things you should notice here is that both dilation and erosion change the shape of the ROI, and the degree to which the shape changes will depend on both the size and the shape of the structuring element. So let's take a look at this with a CT image. So here we have our foam sample again, where it's been segmented, where again, polymer pixels are white and void pixels are black. So if we perform dilation, then what we see is that the holes within the voids are removed and correctly reassigned as void. And additionally, we see that the connections between voids grow. And in fact, we see we've created a new connection between this void and this void that wasn't present in the original image. So we're connecting them together. If we instead perform erosion, we cause all of the holes in the original image to become larger. In addition, we make connections between voids smaller. So this connection is smaller here. The other thing that we see is that we get rid of these small islands in the polymer here. So those false positives for void are eliminated. All right, so let's go on and look at a couple of additional morphological operations. These are called closing and opening. And morphological dilation and erosion are often used in combination, and that's where we're going to address closing and opening. For example, the result of a dilation followed by an erosion is called closing, and the result of erosion followed by dilation is called opening. And let's take a look at this. So again, we have our region of interest with two little sections and our structuring element, the disc-shaped one here. So if we perform closing, then we'll have dilation, which is this black line outlined outside, and then we'll follow that with erosion, and we end up with the final blue shape. So the thing to note about this operation is that the final ROI size is somewhat similar to the original shape, at least more so than dilation erosion alone. And alternatively, if we perform erosion and then dilation, or other words, opening, we see, so the first step is the erosion, this blue line here, and then we dilate again. We do lose the islands in this case, but we end up with one of the regions of this original roid that's pretty consistent with the original shape. So opening is going to remove structure smaller than the structuring element, but again, it's going to be similar. So let's take a look at an example with a CT image. And again, we have our foam sample. And if we perform closing, we see that holes in the void disappear and the connections grow ever so slightly between these. We have the islands in the polymers, those stay. But note that if we do opening, then again, we lose the islands, but the voids inside, the pixels inside the voids or the holes, they stay the same size, unlike the way they did with erosion before. All right, so let's move on. And before I go on to look at other ways to refine segmentation results, I just wanted to have a look at the structuring element shape and its impact on these operations I just described. So during our interactive session that'll happen shortly, we're going to use a plugin called ImageJ. And that particular tool gives you the option of choosing among 8 different structuring elements, which are shown in this slide. So we're going to look at what happens when you vary these among them. So we have disc, square, diamond, octagon, and some lines themselves. So the first thing we're going to look at is the effect of a structuring element and an opening operation using the circle and the square. So first, let's look at the circle. And here we see that many of the voids, they have a roundish shape similar to the original. If we look at the square, we see that now these voids look quite blocky after the opening operation. So they're less consistent in shape as the original. So how about for the diamond and octagon structuring elements? So here's the result of opening for those. And again, here we get some blocky character from the diamond shaped, and on the octagon, they look like they have smooth edges, more consistent with the original roid. Now what happens if we use some of these lines? So we're going to consider the vertical and horizontal lines. And here we're going to see with this particular binary image with circular shaped voids, there's a dramatic effect. And so, for example, with the vertical line, now we see that our void shapes are biased towards the structuring element and they look like vertical lines themselves. And similarly, using the horizontal line, we have horizontal voids rather than rounded ones. And if we look finally at the 45-degree and 135-degree structuring elements and look at the opening, we see something similar. So they're going to be biased in the direction of the structuring element that we used, and they're going to be thinned. So my point is that the shape and size of the structuring element will affect the results of morphological operations. And the point here is that you should consider your choice on your data and what's most appropriate for use. So now let's move on to a couple of other tools. So first, we're going to look at something that's called kill borders. But before we do that, we're going to look at a poll. So that's going to be done by Aya.
Okay. So we have another true or false question. So the statement is, kill borders deletes a user-specified number of pixels on the edge of voids or ROIs in a segmented image. Is that true or false? Coming in pretty fast. I think about almost a half of you answered it. I'm going to give you a few more seconds. It's kind of split, but I think we have a winner. Okay, so that's about close to 70%. So I'm gonna end the poll and share the results. So kill borders deletes a user-specified number of pixels on the edge of ROIs in the segmented image, and most of you think that is true.
Okay,
Okay.
well, let's have a look at that. All right, so it turns out that what kill borders is going to do is it's going to remove ROIs that intersect with the border of the image. It's not actually getting rid of edges of the individual ROIs, or rather it's getting rid of those that are intersect with the object. Now, why would we want to do that? So let's say, for example, that we wanted to do some quantitative analyses. And in that case, we want to ask, what's the distribution of size for the ROIs? And in that case, we don't want our quantitative analysis to be influenced by those truncated ones that intersect the border. So kill borders eliminates them, so prior to some quantitative analysis. So let's look at another tool, and it's called fill holes. And as this name implies, fill holes will remove holes inside of ROIs. And if we look at this example, we see it does a really good job of doing that. However, there's a problem. So if we look at the original and resulting images here, we see that the tool has eliminated a hole that was real. So we had two of these void regions, objects, connected to one another by two connections, and by virtue of that, it filled it. So the thing to consider here is if you have separated objects within your ROI, fill holes is a good tool to use. If you have connected ones, then be careful because it may actually fill the connections between them. So let's go on to our final tool before we work through some examples. Oh, this red circle is just showing you the area that was filled. Now let's have a look at the watershed. So the next tool we're going to look at is called Watershed, and it's going to lead us to our fourth polling question before we dive in.
Okay. So let's start the question number 4. Okay. So the question is, what does the watershed operation do? Does it classify pixels between shapes as a background, or separate objects within a ROI, or creates connections between objects in a ROI? Which one does the watershed operation do?
All
The
right.
answers are coming in pretty fast. I'm gonna give you
Oh, they may
a
know
few
the
more
answer.
seconds.
Yeah.
Second and third choices are doing pretty well. I don't know, because they're kind of pretty split evenly.
Yeah, this is a pretty,
Okay, so most of you answered the questions. I'm gonna end the poll and share the results. So what does the watershed operation do? And the answer is pretty split, like 31, 38%, but
Okay.
creates connections between the objects in the ROI was the winner. Okay.
All right. And it turns out that the correct answer in this case is separates objects within a ROI. So that's what the watershed function does. And I'm going to show you how that works. Okay. So let's say that we have this original foam image in this case. And what we want to do is to separate each of the voids to extract some quantitative information about them. And if we just look at the borders and how the software might see them, then we see here that we have, in this case, one void that actually is a combination of 3. And that's because they're all touching. But what we really want to do here is we want to separate or split these objects apart by these, say, red lines. And we're going to accomplish that by using an algorithm known as watershedding. So let's look at how that actually works. So the watershed transformation separates connected components And here we have each of our 3 objects within, say, a connected ROI. And the way this happens is you assign each of the objects as a basin in here. So we have object 1, 2, and 3. And now imagine that it starts to rain and these basins start to fill in this case. Well, eventually the basins will fill and the bodies of water in the neighboring basins or neighboring objects will start to touch. And the point of this contact is called a ridge line. And we're going to use this ridge line to separate the object by marking those as the edges. And then we can label each body of water as a separate ROI. So we have 1, 2, and 3, exactly what we wanted to do. So how do we transform our ROI into a set of these actual basins? Well, we're going to use a tool called a distance transform, and we're going to see how to do that. So here we see is our original foam image. And if we by eye picked our objects, we'd say, okay, we have 1, 2, 3, 4, 5, 6, 7, and maybe a couple of other small ones. And so we want to separate those into the individual objects. So what we're going to do is use the distance transform. And what it actually does is it computes the distance between each labeled void pixel and the nearest foam pixel. So we have a result of the calculation here. So in the middle of the void, the value is high, so a lighter color in the grayscale. And when you get closer to the polymer, it becomes darker and darker gray, and within the polymer, it's black. And if we plot the 3D intensity of this distance transform image, we get the following. So this plot, you have your 1, 2, 3, 4, 5, 6, 7. And it turns out that each of our objects corresponds to a peak in this surface plot. So it's the exact opposite of what we want. So we need to correct this, and that's easy to do. What we can do here is we just invert it. So we've inverted the values, and now we have, if we calculate the surface here, we see that 1, 2, 3, 4, 5, 6, 7, and here is 6, for example, and it corresponds to a basin, which is exactly what we need in order to do the watershed transformation. So we're going to start filling up these objects and let them fill. And the result of that is going to be this. So on the right side, we see the result. Oh, wow. That's very odd.
What just happened?
It skipped all the way to the end. That's not what we want. Let me
That's a
just
very
go
pretty
back.
picture.
You haven't had the contest yet. Wait a minute.
Yeah, wait, it's not ended. Sorry about that. I have no idea what happened. It's acting squirrely. So on the right side, what we see is the results of the watershed operation after the distance transform. And each of the grayscale, each of the object is colored in a different grayscale, but we see a problem. So circled in this, wow, sorry guys, I have no idea why this is happening. Wow. Okay, so then what we see in this red outline is we have 2 objects. They're 2 different grayscales, but instead what they really should correspond to is a single object. So this is an example of what we call over segmentation, and this can easily be fixed, not to worry. We can merge these objects, and I'm going to show you how to do that today. So that'll lead us to our next part, where we're going to do our interactive stuff. And sorry for the technical difficulties, guys. Okay, so I'm going to minimize this. I have a new share, and I'm going to share this window here. So you should see a blue screen, and you should also see an ImageJ window that I've opened. Do you guys see that?
Yep. So Angela, before we get started
yeah,
on the
let's take some
interactive
questions.
part here, let's take
Yeah.
some questions.
Yes, thank you.
All right. So we've had a few come in. A couple of them here are related to the structuring elements. So what is the width of the lines in the structuring elements? And
Right.
also, what are the sizes of the shaped structuring elements?
Well, in addition, so MorphoLibJ, in addition to allowing you to select the shape, it'll allow you to select the size. So what you're defining is a radius. So for each of the shapes like circle, square, octagon, and diamond, that's a true radius. For the lines themselves, it's really the length of the line, and the line width always stays at 1. You can't change that.
Okay, and then again on the threshold, so the shape, the sizes, you can set those, is that correct?
That's right. So you can set the
Okay.
radius of each of the structuring elements within the MorphoLibJ plugin, and I'll show you how to do that. And actually, it'll show you a small diagram of what it looks like if you'd like to as well.
Okay, all right. Another question here was for the fill holes is obviously it filled in the gap with the polymer and air in the famous earplug. Can you set a threshold of any sort so that it ignores larger holes that are in fact real?
No, not for this. So consider this is a binary image. So the value is either 0 or 1. You have only one threshold you can set. Now, if you're working on grayscale images, there are some tools that allow you to set thresholds when you filter out certain areas. Also, some tools and some other programs will allow you to set a threshold relative to connected things and their size. So for example, you can keep the largest item or the smallest item, but for this tool and fill holes, it's just blindly going to mark the things in the middle and change their value to 0 or 1 or inversely. Okay.
All right. And kind of the last question before we get started, and this isn't really a question, it's more of a comment and just a thought. So it's from Eric says, he's confused with the images compared to how he normally treats binary images. What you describe as inverted, for example, an erosion would in my brain remove white noise, and Watershed would cut at the thinnest part of the white sections, for example, to separate white particles touching. Might need some, maybe Eric, if you can provide a little more feedback here.
Right.
It sounds like white and the black or white and the black are opposite for some people, depending on what you're used to.
That's right. Yeah. Yeah, I think that's exactly true. So you're thinking that to get your basins, then black should be a high value, like you're adding photons or expose an image to photons, it gets darker. Well, in this case, for a grayscale image, black is actually 0 and white is the maximum intensity depending on your bit rate for that particular image. So I can understand how that might be confusing.
And also the target of the morphological operation can be either white or black. I think ImageJ has its own default, but different tools might do different things.
Correct, yeah. So, but I could see where that might get you if you use something that treats it a little differently.
All right, we had one more question actually popped up in the chat here, actually, and more questions coming in. So is there any specific criteria for choosing the structuring element? Is there any tip on what you should consider as your structuring element when you're doing this?
Yeah, sure. So many of the things we looked at today, we're looking at voids with rounded edges. So I would be biased to using a circle or an octagon. If I were working with something that had lettering and I saw some streaks, maybe vertical streaks, then I might use a horizontal one because we know that they're going to get rid of those. So it really depends upon the features and the shapes of those features inside your particular image that you're analyzing. You might imagine if you have lots of lines and straight lines, you might use something like a square or a diamond. So it's just a matter of choice based on your features, shape and size.
Okay, I think that's what we've got so far. So obviously, everybody keep your questions coming in as Angela goes through the real world measurement, real world examples here.
Okay. All right, so again, hopefully you should see my blue screen. I'm going to open a folder that contains our workshop examples. And one of the things I want to mention today is that we're going to look at binary images specifically because we're refining segmentation results. But in fact, you can use this for grayscale images. So in the data folder, I've included the original grayscale images from which the segmentation was done. So you can play with those and see what it looks like or how it's different. All right, so the first thing we're going to do is we're going to look at our earplug example. And in this case, we're going to look at the morphological operations that I showed you. So first, dilation and erosion. So to use the plugin MorphoLibJ, you go to Plugins, MorphoLibJ, and you can see there's lots of different features available. We'll just be talking about a few of them today. We're going to go to filtering, and at the top, you see morphological filters. All right, so we'll click that, and it opens this window. So from here, you would select the specific operation that you want to do. So in this case, if we want to do dilation first, we can select the structural element we want to use. And there are the 8 of them that I mentioned to you before. So let's use the disk in this case. It makes sense based on shapes. Let's change the radius to 2, sorry, to 3. And if we want, we can take a look at the element and we can look at a preview. So here's a preview right here of the circle or the disk that we're using. Click OK, and this is the result. So here we have our original image, and here we have the result of dilation, where these islands that are false values are now larger. Inside of the voids, our holes are missing, but unfortunately, we've created connections between voids that don't actually exist. So now what we're going to do is we're going to ask, well, what happens with an erosion rather. So we're going to change this back here, select erosion, our disc-shaped element because we have rounded voids, change this to 3 and look at what it looks like there. So just like in the example we looked at before, this is exactly how I created that. So in the polymer, we see that those false positives for void are now gone. However, the holes within the voids are now larger. It didn't add any holes, it just kept the same ones and made them bigger. All right, so islands are gone in this one in larger holes. How about opening and closing? So we go to plugins and filtering, morphological filters, and let's look at closing first. With our disc-shaped element, we'll change it to 3 so we can see a dramatic effect and say, okay. So in this case, we're still left with our false positives, but the holes are gone. One of the other things is that the connections are slightly larger because remember, we're doing that dilation first, and we also create connections between these others, but the shape is more consistent in size than was the dilation by itself. So we go to plugins, MorphoLibJ filtering, and instead this time we do closing with 2 and a disc, let's see, 3, disc shaped, and okay. Then we see here that, oops, I did the wrong one, guys. Let's go back and go here and select.
You always have to make the window you want to operate on active before you do this in ImageJ.
Yes. Okay. Yeah. Have I had the wrong one? Yes. So here we go. All right. So now we see these little islands within the polymer. They're gone. And as a matter of fact, so are our holes within the voids. And that's because we're following it erosion with the dilation. So that kind of gives you an idea. But again, we still are stuck with these extra connections between our void pockets that we don't want. All right, so let's look at a couple of other filters. So in this case, we're going to use, let's say this one for the first one, and we're going to go to Morphological filtering. And on the bottom of this list, you're going to see kill borders and fill holes. So if we say we want to kill borders for this image, then what we see is we get rid of most of them, right? Because our voids, many of them are intersecting, with exception these really tiny ones in here. And alternatively, if we use this on fill holes, plugins, got to select the window, filtering, fill holes, then we get the voids, their holes are filled, but so is this one here. Let's look at a different image on this example. So let's look at some segmented bamboo. So in this case, we have a lot more voids. So we're going to try to kill the borders, and we would expect that we get rid of these truncated ones out here, but the majority of them will stay. So we go to Morphological, filtering and kill borders, and we get this image. So if we wanted to do some quantitative analyses of these void pockets that are here and ask how large they are, the calculation won't be biased by those that are truncated because they intersect with the border. And if we look at our fill holes, then what we see is some of these in the middle here that have some holes within them, those get filled, as do some of the ones over here. So that just illustrates in a different example what happens in that case. All right. So what we're going to do now is we're going to move on, and we're going to look at our watershed operation. So I showed you in the presentation that how to do the distance transform, and then we did the watershed. Well, it turns out that Morphological will let you do each of these steps independently, or you can do them all at once. So for example, in plugins, Morphological, we can calculate an operation on a binary image. And in this case, we can go directly to distance transform watershed, where it combines both actions. If instead you wanted to calculate a distance map and then go on to perform the watershed, you can do that. So these operations are up here. But we're going to go straight for the distance transform watershed. And in this case, we're going to preview exactly what happens with some of these. Remember, our output is going to be a grayscale image. In this case, it's 32 bits. And this is the output that would happen with the chessboard distance. And it turns out that if you select different distance map options, what's going to happen is you'll see the separation lines within each of these changes slightly. So more straight lines, or for example, it might be more curved in the case of this quasi-Euclidean. It does some weird stuff though for areas that might have some voids within some of our roys. There's this one, I'm afraid I don't know how to, is it Borgafers? Let's hope I pronounced that right. And there's Chestnut. So we're going to use the city block in this case for our example. And we're going to turn off preview, and we want to output our image. All right, so now we see the result of the distance transform plus watershed operation, and we could see it did a fairly good job, but there are some examples of over segmentation. Let's look at those. So in the top left, we see there are a couple of different objects that have, if we look here in the status window of ImageJ, if we hover over the top one, it says value equals 44. And that's the index number for this particular object that was separated. If we look at the bottom one, it has value 50. So where this one should be a single object, it's separated it into two. The same thing is over here in the middle towards the right. 110 is its index, 114, the one on the right. Instead, they should be a single object. And there are a couple of others. So how do we fix that? Well, that's easy to do. And there's a tool for that in Morphological. So if you go to Morphological, label images and label edition, you'll get a new window. And what we'll see here is now we have some tools on the left that allow us to merge these over-segmented items. So it's simple to do. You just click on the two that you want to merge, click merge, and you'll see a log window that says it's merging 50 and 44. We can just repeat that, for example, for a couple of these that are over-segmented. How about this one? There's 3, we're going to merge those. This one is 2, and we're going to merge those. And we see that those 4 examples got merged. But one of the things you'll notice is that the lines between these two does not go away. And however, if we hover over them, we see that they're both labeled 44. So in fact, they were merged, but visually the line is still there and present between them. All right, so what do we want to do next? So let's say we want to do some quantitative analyses, but again, we don't want our void area calculations to be biased by those that are truncating the edge of the image. Well, you can kill borders. And in this case, in the label addition window, it's called remove in border. So if we just clicked on that button, then we see those are now gone. So now that we have merged our over-segmented objects, then we can go on to do quantitative analyses. So to do that, we go back to our plugin, and then there's an analyze tool. And at the top, we're going to say analyze regions. And you see that there are a number of different things that we can calculate in this case. So for example, you can do all of them, we can do some of them. It's really simple to turn them off. You just simply uncheck them, and the output table will eliminate those. So I'll leave a few of these checked and say, okay. And you see that calculation takes pretty quick. So here we have our table, and on the left is our label corresponding to each of the labels that show up in the status bar. So 72 is this large one. If we wanted to look at the area, we could scroll down and say, okay, this is 72. And the area is 13,966 microns square. Okay. All right, so what if we wanted to sort these in some sort of order? You can do that. So if you right click and click sort, then you can choose which particular parameter you want to sort by. And if we just click area, okay, then we see that the smallest one is at the top and the largest one is at the bottom. And it turns out that's 72 that we just looked at. And the MorphologiJ plugin is always going to sort these from smallest to largest. There's no way to do it in the opposite way that I know of anyway. If you know how, let me know. All right, so now we have all of this information, and then we can export it and look at some distributions of the various areas. And let's say that at this point, what we wanted to do is to put this example image into our notebook. Well, this grayscale image isn't so great. Perhaps we want to use a colored image. And it's quite easy to do that with MorphologiJ. So if you go here and go to label images, you can change the labels to RGB. And when you do that, you have a number of different coloring schemes that you can use, like lookup tables. If we just say mixed colors, for example, now it's going to switch the background color to white, and it's going to color each of the objects as a different color, and it's just going to shuffle those. And click OK, and here's what we end up with. All right, so now we see those that we merged together. They're all the same color at least, but the line is still there. But one of the things I want you to notice is that let's hover over this number 72 that was the largest. If we look in the ImageJ status bar, you'll see its value is now 255, 255, 000, and labeled yellow. Well, by virtue of converting it to the RGB, you lose all of the labels. So you cannot, in fact, take this image and do an analysis on it. It'll say, I don't think so, I need labels. But it does make for a better picture, say, to put in a report or your notebook in particular. All right, so those are the things that I wanted to show you today. Hopefully you learned some new things about these tools. And what I want to do at this point is go back to our PowerPoint presentation. Hopefully you see that.
Yeah, we do.
And the things we just covered today are asking the question, why do we need to refine segmentation? We asked the question, how do you do that? And finally, we looked at a tool, a plugin called MorphologiJ that showed you how you might refine them, your different ROIs, and do some further analyses. All right, and with that, you stuck around long enough for the game, and I'm going to hand this over to Aya, and she's going to do this.
Okay.
With, Tom.
So I can see that some of you are eager to get the compensation or the gift card. So let's get this game started. It's a pretty simple game. If you were here the last time, you probably remember. But let me start the polling question. So you should see numbers from 1 to 6. And Tom has a die in his office and he's going to roll it. And if the number he gets matches the number you choose, you will win a $30 gift card, which we will send you by email. See, 4 is popular again.
That was the number everyone picked before, right?
Yeah, we didn't have many people picking 1 and 6, and everybody
Yeah.
picked the 3 and maybe 4 and 5, I think.
Yeah. All right, Tom, you know what that means. You need to roll a 4.
No pressure. Yeah.
No
Nope.
pressure. I'm going to give you a few more seconds to think about it.
Yeah, everybody vote.
I don't know if thinking about it harder would give you a better
No.
chance, but it should be purely statistical.
Yes, agreed.
Yeah, I think most of you voted. Is everybody in? I think you're mostly in.
I think that's all of them.
Okay,
Yeah.
good.
What? Okay, I'm gonna share the results. And in the poll
Right,
to share
let's
the
see.
results. This is pretty much the same thing we saw the
Wow.
last time. We
Yeah.
don't
Okay.
have
All
a
right.
lot of people voting for 1 and 6,
Interesting.
but we got lots of 4. Okay.
All right. So I'm just going to
That's-
drop this on the
yeah.
floor so everybody can see it live.
No cheating.
Let me get the camera. And it is a
So
It's
one.
1 again.
What? All right.
Okay,
Wonder if it's the same 3 people that won last time.
maybe.
I think only 2 won last time.
And Eric is correct. It's a Gauss. We're seeing a Gaussian distribution here.
Yes, we are.
Yeah, we are, Eric. And it's quite similar to what we had last time. So
It is a similar, yeah.
I wonder if we
Yeah.
ordered the numbers differently in the poll, we would see a different distribution across there.
That's
You know
possible.
what? We can
That's
try
possible.
that.
Maybe next
Okay,
time we'll
so
do that.
if you voted for 1, you know that you won, and we will be sending you the gift card. Congratulations.
Nice. Congratulations, guys. All right, so congratulations to our winners. And with that, we're going to wrap up, but we have a few minutes for some questions before we go.
Yep. So we have had some questions come in. We do have, again, just a few minutes to get to them. So I'm going to pick a couple here, and then the other ones, there's 3 that are the same. So I think, and they can be responded, I think, offline is best. So Peter asks, and he's looking at cryotomograms, which show actin bundles as features of interest. So again, this might be an offline answer, but just some thoughts. So he needs to segment and then create a 3D representation. So he's used IMOD and EMAN and has some preliminary segmentation, but he's having trouble in getting 3D. So he's really looking for some advice. And again, this might be an offline conversation, but
Okay.
it's a very interesting question.
Right. So that is an interesting question. And I am less familiar with IMOD and EMAN. EMAN, I think I used in my earlier, there's a program similar called EMAN for crystallography days, but I haven't used those tools. Inside of Fiji, there is a 3D representation. And I'm just opening that software. I'm going to show you just real quickly where it is. And even where is it under? Just plugins. Okay. Here, can you see this now?
Nope,
No.
You can't see it in here?
because you're sharing the Q&A slide.
Yeah, it should
You-
be overlaid on the Q&A slide. What if I say,
You
You
might
can't-
need a new share.
all right, let's do that then instead. But I just
Oh,
want to
there
make
it
sure.
is.
Oh, you
Yeah,
see it now?
Yeah,
Okay, I just want to make sure that I show you where it is in case you want to try it with ImageJ. The great thing is ImageJ is free. So there are 3D plugins, a 3D viewer that comes, I believe, with the Fiji the Fiji distribution of ImageJ. And if you click on that, it'll give you a 3D rendered volume of what you've segmented. So you might try that. And then there are some other programs that do really beautiful 3D rendering in that case you might try. And one of those is Dragonfly. Our workshop series will move to that later in a couple of months. So we'll show that as well. And perhaps I can touch base with you offline and we can navigate that in more detail as well.
Okay, and then the last question is, does MorphoLibJ work on stacks as well, such as processing 3D data?
Absolutely. So again, in here, what you'll see MorphoLibJ is for filtering, you have a morphological filter and a morphological filter 3D, and that's the same for many of the different tools within MorphoLibJ. So if you're working on stacks, you'd use the 3D option. I just use 2D images for expediency for time today.
Okay, so I think the other question is, there's 3 questions asking what can go wrong with segmentation. I think we showed some of that in the examples. I think that's just, that's more conversational. So I think we can kind of continue on because that could take a little too long, I suspect.
Well, and I could just say everything could go wrong.
there
That
are many
seems
things
about
that can
right.
go wrong.
Many things that can
Seems
go
about right.
wrong. So an example today, eventually I was looking at something where they were 2 distinct objects, but they had similar grayscale, and thresholding was not going to work. Machine learning didn't really work so well, but deep learning worked. So if in fact, so you can separate both on grayscale and on shape and in location in the image. So if you're having challenges, you might try deep learning to see if it works. And good luck with segmentation. It can be hairy sometimes.
Okay, so that's all the time we do have for questions. And again, if you have further questions, you can reach out to us directly through the website. So as I said earlier, a recording of the webinar will be available tomorrow. An email will go out to all registrants with instructions on how to view the recorded presentation. And links to the resources mentioned today will also be shared on the landing page. All right, so we'll be hosting another interactive webinar focusing on demystifying reconstruction using ImageJ on Wednesday, May the 11th at 2 p.m. Eastern, 11 a.m. Pacific. We look forward to seeing all of you then. Thank you for joining us, and we'll talk again in May.
Bye, guys.
Bye-bye
Thanks
now.
for joining.